I'm Sergio Fantini, Professor of Biomedical Engineering, and I've been current advisor for Giles PhD. And other committee members include Pauli Malidi, also from Biomedical Engineering. Then we have an outside of the department member, Professor Fushi Ero from Electrical and Computer Engineering. And then the outside of the university member of the committee is Professor Steve Jacques from the University of Washington. And Professor Jacques, Professor Aaron are connected via Zoom. Professor Malidi is here. So the structure of the defense is that Giles is going to talk for about 40 to 50 minutes, something like that. And then there's going to be an opportunity for the audience to ask any questions. There's going to be public Q&A. And then after the audience is done with the questions, then the audience will be excused, and we're going to have a closed session of questions and answers of the committee with Giles, and then there's going to be a decision. But just wanted to say that it's been a pleasure to have Giles in the lab for the past 4 or 5 years. It was really great to present lots of work. So actually, also look forward to this defense. And with that, Giles, all yours.
Well, thank you, Sergio, for the introduction. And my thesis is titled Enabling Heat Region-Specific Optical Measurements in a Diffuse Medium with Near-Infrared Spectroscopy. So that's like a lot of buzzwords with specific meanings for certain pairs of words, but hopefully by the end of the presentation, you understand what it basically means. But the defense is going to be split into 3 main parts, and the title is mainly referring to the first part. So that's enabling heat measurements. And then I apply the techniques that I developed in the first part to cerebral hemodynamics, so brain blood dynamics, basically. And then in the last part, we apply the same technique, but using a different advantage of it to spectroscopy. But before we get into the main parts, I'm going to just briefly introduce the kind of concepts I'm going to talk about. So this is the introduction. And the first thing I want to introduce is just where we're working, which is the optically diffuse medium. And the 2 main properties that we're concerned about in the optically diffuse medium. So when light enters the diffuse medium, that's like your tissue, it scatters around in random directions and then ends up having an average distribution from millions and billions of random scattering events. And the quantity that we use to describe that would be the reduced scattering coefficient. So that's the first quantity we care about for the diffuse medium. The second one, which is more of what we focus on, is the absorption coefficient. So this is what we're actually trying to use and measure. So this is, instead of how the light moves around, this is how the light is killed and absorbed inside. So this is important for tissue because in tissue there are different spectra of absorption for different chemicals inside your tissue, such as different species of hemoglobin and water. So the reason that it's called near-infrared spectroscopy, which was the last term in my title, is because the absorption in tissue is low in the near-infrared light range. So we're working with light that goes from about red to infrared where you can't see it. And you can see that visualized here by this is the average path before a photon is absorbed. And you can see it can travel longer in these red and near-infrared regions. So this is the light range we're focusing on. So now I've just introduced the 2 quantities we care about, which was reduced scattering coefficient and the absorption coefficient. And now we're going to talk about the measurement technique that I use, which is frequency domain near-infrared spectroscopy. So FD near is usually what we call it. And what we do is we inject sinusoidally modulated light into tissue and then detect some distance away from the injection. And we're detecting the amplitude of the sinusoidal oscillation. So we'll call that the intensity. And then we're also detecting the phase shift from some reference of this oscillation in asphalt. So the two main things we're concerned about are intensity and phase. And if you measure calibrated intensity of phase, you can get your absolute absorption and scattering coefficient. And then if you measure dynamic changes in intensity for phase, you can get changes in the absorption coefficient. So this is the method that mostly is used to like measure dynamics of blood concentration. So this. So that's it for the introduction. And now I'll move on to the actual need, which is enabling deep measurements. So we need to motivate the reason that this is even a problem, right? So why do we care about achieving deep measurements? Well, the reason is because typically when you make this sort of measurement with the source and then a detector at some distance apart, so in this example, it's about 35 millimeters, which is reasonable. The region where the measurement is coming from is very close to the surface, so it really only penetrates. Usually the rule of thumb is 1/3 of this, so you could say it's like 10 to a little more than 10 millimeters. So it's just barely touching the brain. So if you want to measure hemodynamics of the brain with this kind of measurement, you're going to have problems because a lot of your signal is coming from the skull and the skull. So this is where the need to develop preferentially deep measurements comes from. So there is basically a whole journey I want to go on here that eventually leads to the technique that we do develop, which is called dual slope. But along the way, we started with using different source detector distances. First, so when I say different source detector distances, what I mean by that is using different numbers here. So like from 10 to 40 millimeters instead of just 35, for example. So this is talking about short versus long source detector distances. And now we can see how that region changes based upon which source detector distances you choose, right? So if it's short, you are measuring something more superficial. This blue region is the short one. And then this longer one, which is 42 millimeters, is a much, much deeper region. And these regions just represent where the signal to noise for a particular perturbation that I've chosen is greater. So it's basically where you can measure. And I'll say the approximate brain depth is about 10 millimeters. So really you need to be out in this range of distances, like beyond 25 millimeters, to get some sensitivity of the brain. Now, this is for intensity measurements. But remember I said that we measure two different things with frequency domain. We also measure phase. So you can use phase to measure the changes in absorption in the medium instead of using intensity, which is what this is showing. And now you can see that each one of these regions of the same color of the intensity is a little deeper. So phase is actually just a little bit better at penetrating deeper inside the medium than intensity when you're looking for absorption changes. And this is caveated by the fact that phase is a more difficult measurement instrumentally, so there's more noise. And that's primarily the reason that the field is focused on intensity. So you can use a measurement from one source to one detector, which is what I'm showing here. But now I'm going to move on to using multiple detectors and one source instead of just one pair. So what I mean by that is, say we have one source and two detectors. So now what we can do is we can measure the function of what either our intensity or our phase, like what we care about, versus source detector distance. And in a homogeneous diffuse medium, we get these curves. But notice that this is a more complicated relationship than just the intensity. It's something that's linear to make it a straight line. So, okay, so now what we're going to do is we're going to measure at two source detector distances, and we're going to measure the change in phase between those two. And we know the change in distance, so then you can get the slope. That's the phase slope measure. Same thing with intensity slope. There's a change in this linearized intensity, which is the change in the source detector distance, and then that's the change in the intensity slope. Right? So we could use calibrated absolute values of these slopes again to get absolute mu A and mu S prime. Or we can get changes in these slopes from the baseline slope to get changes in mu A again, which then gives you mu vector. So this is basically the method that I'm going to be moving forward with, which is using changes in the slope. So let's look at what the sensitivity regions look like for slopes instead of single distance pairs. So now it's much more complicated. And essentially what you've done is you've subtracted away the common octave. So in this case, the detector is the common octave. And for example, this orange one is the slope formed between this source and this source. We subtract away the detector, we're left with this region. So we still have some superficial, we remove some. The caveat is now there's negative sensitivity. And what negative sensitivity means is if the change is in one direction here, we measure the opposite direction. So that's bad, it's like an arc. The same thing that I said about phase is true here too, where in general it's deeper. And then the same thing I said about source detector distance is true too. So if you use a pair of distances that are longer, it is deeper. This blue one. So this is basically the work that influenced the development of the main technique, which I'm going to be talking about, which is dual slope. So now I've compared basically what we call a single distance was the first thing I said. Now we're doing single slope. So then finally what we do is we move on to dual slope. And I need to explain what that is because it's essentially two slopes, but with very specific requirements. So first, let's step back from the sensitivity regions and just look at what a dual slope probe is. So what I showed you before would have been only 1/2 this, where basically you can measure from the source these two detectors. That's a single slope. And you can see this right here. 1 AB, 1 AB, that's a single slope. But then we can have a symmetric slope on the other side by just placing a source here, 2BA. So essentially all that dual slope is it's the average of these two single slopes. But there are specific requirements for what those single slopes need to be. And the requirements is that the short octave for one slope has to be the long for the other. And that's probably one of the most important requirements. So what I mean by that is detector A is the short for this side, right? But detector A is the long for this side. So now you can see why you basically need a symmetric set. You can't like place this over here and measure two slopes on this side. It needs to be some sort of symmetric set. So that's an example of dual slope probe geometry. But why? Well, not why, but first, what does this averaging of two slopes do? So now we have these two slopes again, single slope 1 and single slope 2, that form a dual slope. And they're going to measure some slope of this measured data versus source detector. But of course, because of instrumental factors and all that stuff, the slope it measures isn't going to be the theoretical true slope for the diffuse medium. It's going to be shifted somehow. So that's what's shown here with these dashed lines. And because of the symmetry, the effect that one of these coupling factors has on one side has the opposite effect, the opposite slope on the other side, which makes it so that the average of the two is actually the theoretical slope. So that is the first advantage of dual slope. It basically means that the dual slope is representative of the theoretical slope for the homogeneous diffuse medium. And then what that means is it allows you to make calibration-free measurements. So this technique was originally developed in the 90s to measure the optical properties of the medium without calibration or adapting. But we extended it from that. So one way we extended it is thinking about using it in terms of dynamics instead of just absolute properties. So since the coupling factors are canceled out, that also means any artifacts that are dependent in time. So this is an experiment. We have this dual slope set here. And what I've done is I've literally removed the fiber for detector A from the instrument and then replaced it. So any single distance measurement that is measuring using detector A, that would be like 1A or 2A, measures this massive change in absorption. And these numbers are very much not realistic. And then that change in absorption is gone when I replace it, but imagine like you have this situation where the probe contact changes a little bit. This would also cause an artifact here. So now if we move on to those single slope methods that I mentioned, the artifact is still present, but notice how it's in the opposite direction for two diffuse measures. This is what I was talking about where it affects it in opposite directions, right? And then finally, dual slope is gone. So this is basically what I would call the first advantage of dual slope, which is that it suppresses artifacts and drifts in the signal. Now for the second advantage of dual slope, the second advantage of dual slope is that it is preferentially sensitive to deep within the medium. So do you remember that when I showed those single slope traces, single slope regions, we got rid of the sensitivity near the common optic. Well, now essentially all of the opticals are common opticals for some singles. So we're getting rid of a lot of sensitivity on the surface and we're leaving the sensitivity deep within the. So this is where the positive sensitivity is for intensity, and this is where it is for phase. But there's still this slight negative part. So now I just want to pass around the first set of props now that I've introduced all of these different data types. So I'll start here, go backwards. So on the back of these 3D printed things, it says what data type it is. And what we have is we have these single distances, single slopes, and then dual slopes for intensity and phase. So it's actually the 3D version of this because this extends out into the medium a little bit. And well, you guys will look at those. I'll show you this. So this is what I mean by the 3D version. This is just the cross section up through here of this nut. So traditionally, you would call those bananas shaped things where they single distances bananas. And then we name this nut. So you can see that the full picture isn't really seen just by this cross section because this nut actually extends quite a lot out of the floor. And it's actually extending out of the floor for more than this side. So now that I've shown you all these different sensitivity regions and I just showed them as like Boolean maps, I want to also now show that I can give you a quantitative measurement of sensitivity instead of just the region because how important later. So these maps were generated by threshold, like the previous map they showed, were generated by thresholding the actual sensitivity. So we actually know how well the array, the particular type of measurement, will measure everywhere inside the medium, down to an actual quantitative value. And this sensitivity is basically the ratio between what is measured and what is actually inside. So you can see why if that's negative, you're going to measure the opposite direction. So this is important because this is essentially the Jacobian And the Jacobian is what you need to do linear imagery construction, which I'm going to talk about. But you can see that sensitivity is exactly what I said. It's the ratio of what you measure to what is truly the perfect. And then finally, now that I've introduced all these data types, single distance, single slope, dual slope, intensity and phase, I want to show you just one easy way to compare, which is assuming that you have a perturbation that's layered instead of a perturbation that's voxelized like the last image showed you. Now, what we can do is we can show the sensitivity to each layer. So that's what this first one is. So it's assume you have these 0.1 millimeter thick layers. What's the sensitivity to those? Then the second one is saying that set a certain Z depth. What's the sensitivity to below that? So I'll focus on the second because that one is easier to understand. Because basically what we want is you want to have high sensitivity to any depth that's deep and everything below it, right? So you want these curves to be stacked up here. So this is like saying that dual slope has the deepest sensitivity, then single distance phase, then dual slope and intensity, and the shorter version of single distance phase. And then these are the single distance intensities. So you should think of it like this. Traditional nearest measurements use this one, and now we're going to try it. Okay. So that's significantly deeper inside. Okay, so the first thing we apply dual slope to is imaging. So that's the reason that I was introducing the quantitative map for sensitivity, because now that we know where the measurement comes from inside the medium, if we have a particular measurement, we can reconstruct what it looks like inside the medium. So if you want to build a dual slope imaging probe, there are many steps you need to go through before you use it. And that's what I'm going to talk about in the first couple of slides here. Because dual slope has complicated requirements. So you can't just like put sources and detectors in random places and then measure to see them and call it. So one thing we did is we developed an algorithm, which is just kind of visualized here, which finds dual slope sets inside a source detector array. And it does that by basically applying the three requirements that are now formalized on this slide, and I kind of hinted at before, and two constraints which are based on instrumental limitations. So the requirements is that dual slope is two single slopes. No. The single slopes have to have the same difference in source detector distance. So if you're measuring source detector, the difference between those detectors needs to be the same, both single slopes. And then that symmetric requirement I mentioned earlier is the third one. Okay. Constraints are based on the instrument. So the first constraint limits how long these source detector distances can be. So we don't want it to be too short, and we're not probing deep. And we want it to be as long as possible, but limited by influence. So 40 is kind of reasonable. Then this is more the limit on the difference between the source detectors is limited by the dynamic range. So you actually have less noise in the measurement of absorption because it's a larger source detector difference. But then the dynamic range starts to hurt you from those detectors. So this is the first method we use to design a dual slope array. So let's say now that we have this array of source detectors and we've got a dual slope set on. Well, we also want to refine the exact positions of those sources detectors. So we developed an algorithm that applies like pseudo forces between sources and detectors to then homogenize all the source detector positions to approximately those goal source detector positions. And basically what that does is it makes it so that the array has all the same short distances, all the same long distances, and then it has to have all the same differences. And then finally, we want to evaluate how good this array would be at image reconstruction. So shows an image reconstruction method, which is the more pseudo-inverse, which is basically a way to invert a system where you have much less measurements than things you want to recover. So it's a lot of voxels, very few measurements. So remembering that the sensitivity is essentially this from the equation I showed before, we can write this forward model where all of your measurements, this would be like 30, is some matrix times all of the boxes, this would be like 10,000. So then you invert that sensitivity matrix to get your reconstructed. So what's important is that the actual reconstructed are not the same. So the imaging system can be described through this transform, where it's the pseudo-inverse of the matrix times itself. So this is the key point, right? Because this is what's true, this is what you get. So what we did was we did a lot to examine this matrix here. We want that matrix to look like the identity. So the first thing we did is we invented a metric called reconstruction, which is related to the diagonal. Because the identity has diagonal. Then the crosstalk metric is all the off diagonal. But an identity should have all zeros. And then finally, you may realize that this is in the rows and columns of this symmetric matrix are the impulse responses. So because of that, I was able to develop code to, in one step, calculate the resolution and localization for every voxel position inside. Resolution being how much a true perturbation is spread out, and localization being how much you reconstruct it in the wrong location. So now that we have all these methods to design an array, let me show you the first array that we use. So this array was used for phantom measurements. Phantoms being like things that have the optical properties of the tissue but are not. So this was an array with a circle of sources and a circle of detectors, and then it made 16 dual slope sets in total. And the sets all look like this. So we have what these are called linear asymmetric sets, and then these are called trapezoidal sets. And this kind of are rotated around. So we put this array on a phantom with these optical properties, and then we put perturbations inside that phantom with these changes in optical properties. So this is simulating kind of a reasonable change in absorption that you would get physiologically. And we put perturbations in two different locations. We put one deep, below 10 millimeters, and then we put one right on the surface. So the goal here is you want to reconstruct this one and not be confounded by this one. Most measurements, single distance measurements in the field would be confounded. So these are the results from that experiment. And we have the three scenarios, which is when you only have that superficial perturbation, which is in truth on the right side of these plots. And when you only have that deep perturbation, which is on the left side of these plots, and then when you have both. So we were able to simulate what we expect, which is what this theory column is. And then we actually have the experimental results, which are this experiment column. And essentially, what is good is if we can reconstruct the deep one, but not the superficial one when they're both there. And let's focus on this last row. So dual slope intensity in the experiment reconstructed something on the right side, which was superficial. However, dual slope phase reconstructed something on the left side, which is the deep. So we'll say that dual slope intensity in this experiment was confounded by the superficial perturbation of the dual slope phase preferentially reconstructed. So now we've kind of shown that the sensitivity maps we developed with theory are true at least on the hand. So next, we want to apply these imaging methods to in vivo experiments. So we developed a much larger array, and this array was evaluated using those methods I showed you before to get this kind of complicated shape, which is physically. So this is the physical size of what you're seeing on. And this array resulted in 30 dual slope sets with the goal of being large, but not caring as much about resolution or localization. So we evaluated this array to make sure that we achieve the goal. So these is the rest of the reconstruction map, which you want high values for this one. The cross-section map, which you want low values for. And then resolution and localization. So by looking at these maps, if we see right here and here, it is low values of reconstruction and crosstalk, that means it's black spots there. However, there is high values of reconstruction in this point, so that's the point where reconstruction is going. So these are the kind of conclusions we draw. Now, if we go look at the resolution and localization, we can just get an idea of how well it performs overall. So overall, its resolution is approximately 25 millimeters, but its localization is rather good at 5. So we achieved the goal we do. So we had to build this array after we designed it on the computer. So we developed this mold design where basically each source and detector needs to be located in a very specific position. The way that we located the specific position of the source and detectors was by passing them through meshes, which have the source and detector position as holes for the source, for the fibers to pass through. And then this was all fixed and held inside this clamping mold. So this mold clamps like this, to hold all the sources and detectors in their positions, which then allows you to put down the mesh and then pour silicone. And then that resulted in that array that I held up. So we did an experiment where we did visual stimulation on a human subject, and the array was placed over the occipital lobe. So basically what that means is that this array basically put right here, strapped on. And then the subject sat and watched this circular checkerboard flip between these two images at 8 Hertz for these orange periods of time, and then was just resting for the white periods of time. So from doing this sort of experiment, you can average all the time periods together to get the average response for that stimulation. And we can do that for all 30 of those dual slope sets in that array, and then also reconstruct an image of the hemodynamic during this protocol. So these are the 30 dual slope sets in that array, approximately showing where it was location-wise. And the occipital lobe is basically this upper portion. So we expect to see a response. The expected response is an increase in oxyhemoglobin and a decrease in DO, which is exactly what we see, and it's a localized to a specific location. Now, if we compare the different data types, this is the relationship, which is that the amplitude of the change is the least for single distance intensity, which is the traditional measurement of the field, and the most for dual slope phase, which is the measurement that we are developing. So finally, what you can do with this dual slope imaging approach is you can take all of these traces and then make an image of activation. And that's what we've done here. So these are on the same scale. And already you can see that what I said is essentially true, where this activation amplitude is larger for dual slope phase than for dual slope intensity. And you can also see that it's localized to the upper center part of the brain, where it should be for the visuals. One other negative part of phase I want to point out to here, which I kind of hinted at earlier, is that we have less data, especially on the edges of the brain, because there's less good contact between the skin and the opticals on the edges. And phase is a difficult measurement instrumentally, so more noise, we had to eliminate the sense on the edges. Okay, so that is basically the first part of this. That was the part referring to heat measurement. So now I'm going to move on to cerebral hemodynamics. And you'll notice that there were few experiments in the first part. It really only showed one on a phantom and then that image. So now what I'm going to show you is all those different techniques that I introduced in the first part, but applied to brain. And we'll focus on the hemodynamics themselves. So first I want to introduce coherent hemodynamic spectroscopy, which is the method we use to look at hemodynamics in the brain. So we are concerned with hemodynamic oscillations, and we think of hemodynamic oscillations as phasors. So see these three time traces, these are the important ones that we care about: oxyhemoglobin in red, arterial blood pressure in green, deoxyhemoglobin in blue. Now, you can see that there's a phase shift between these, and there's also different amplitudes. So we consider those phase shifts as different angles of some phasor, and the difference in amplitudes are different lengths of those phasors. So we have models that relate these phasors to each other and then give you things that mean real hemodynamic quantities like blood volume. And this is an example of such a model. So I won't go into every particular piece of it, it would be too much for right now. But essentially, the oxy and deoxy, which are measured, are this one and this one. So these represent the amplitude and phase of oxy-deoxy oscillations. And this is the amplitude and phase of the arterial blood pressure oscillation. Now, we think about the phase of a blood volume and a blood flow oscillation, and then also the components of oxy-deoxy that belong to flow and the components of oxy-deoxy that belong to volume. The important part is that flow oscillations are out of phase between oxy-deoxy and volume oscillations are in phase. So now what we've done is we've just simulated, pseudo-simulated, an impaired autoregulated support brake function here. And we've moved all of these phasors around to simulate that. And now I've put black arrows on the two things we actually measured. So you can see what happened is that the deoxy got closer to oxy and oxy got lower. So when you're measuring phasors, you really need to compare two of them. You just really want, they're actually oscillating, they're not really vectors. So you make them into vectors by taking their ratio with another phasor. So the two ratios we care about are total versus arterial blood pressure and deoxy versus oxy. And in this experiment, simulation, what happened is that the phase between deoxy and oxy got closer to being in phase, and the phase between total and arterial blood pressure did not change much of the amplitude. So this sort of change could be consistent two things, but the one that I'll focus on, which is more intuitively makes more sense, is that if this vector moves from this direction to this direction, it goes from blood flow, because remember these are out of phase, to blood volume. So I'll be talking about blood flow versus blood volume dominated oscillations, which basically means blood flow out of phase, blood volume for the opposite. So if we go to an actual measurement, how do we measure these phases? Well, we need to have some sort of hemodynamic oscillations, right? And those oscillations need to be large enough that you can measure them. So what we do is we induce oscillations in the arterial blood pressure. And there are two ways we can do that. We can do that either using pneumatic thigh cuffs. So literally massive blood pressure cuffs that go around your thighs and inflate and deflate at the frequency we care about. Or we can ask the subject to breathe at the frequency we care about. So this is an example of a time trace that did both of those. And you can see that blood pressure oscillated at the frequency we expected. And then different data types also showed oscillations. See the oxygen going at these frequencies. So then we can do signal processing to find those phasors for those oscillations at that frequency and then do our CHS analysis. So what's very important for CHS is the last point in the CHS acronym, which is code. Sorry, the first point in the CHS acronym, which is coherence. Right? So this is the part of the CHS analysis that I did work on, which is finding when those oscillations are coherent. And what do I mean by coherent? Well, coherent means that two signals are coupled together such that the amplitude and phase changes. And that means that you have to be considering signal pairs when you talk about coherence. So the signal pairs would be between some blood oscillation and arterial blood pressure. So here we're talking about oxyhemoglobin versus arterial blood pressure. And then you can measure the coherence between the two as a function of time and frequency using wavelength, which is a type of signal processing that is similar to Fourier transform, but also is time involved. And if we look at just one frequency, we can then plot that coherence, which goes from 0 to 1, but I'm only plotting about 1. But what does that value mean? And that's the important part. We need to find a way to say when the coherence is significant. So essentially, when you do hypothesis testing, like t-test, what you're doing is you're comparing the value you get, the t-score you get, to a threshold value. We need to do the same thing. We need to compare the coherence value we get to a threshold coherence. And to generate that threshold coherence, what we do is we have random data that we calculate the coherence between the two signals, and then we find the 95th percentile of those coherence values, which then gives the threshold. Now, all that being said, this is a very difficult problem for wavelength because the map of coherence is two-dimensional. So if you're going to find the 95th percentile of something that's two-dimensional, you need to make a large three-dimensional array and then sort every single two-dimensional plane and then find a 95th percentile. So I developed an algorithm that approximates the 95th percentile in a memory efficient way. So you don't need to keep all of those long samples. Instead, what it does is it just saves the coherent samples around the 95th percentile and throws the extra ones away. And then it estimates the 95th percentile as the central plane inside that three-dimensional array. So this allowed us to then create 2D maps of the coherence threshold that we need to determine when something is significantly coherent, and then carry on our CHS analysis, which tells us which times and frequencies we should average to find the phases that we should have looked at in the first plot that I showed you. Okay, so now I'll show you the actual experimental results of these methods. So first, I'll show you the CHS results for what I'll call multi-distance experiments. So these are experiments that use single distance and single slope, similar to the first figures I showed you that had the bananas at different depths for different distances. Those bananas at different depths for different distances were inspired by this sort of probe, which was used to measure hemodynamics for cuff and breathing oscillations at 0.1 hertz. And we analyzed the data from this probe for all 7 of the single distances, density and phase. And then also 5 single slopes, which are different by 10 millimeters. You can see it's one there, but only for intensity. The reason that phase was excluded from the single slope analysis is because it's too noisy. Single slope is a noisier measurement than single distance, and phase being noise and intensity makes it to the point where you can't really use it for a single slope. So here's an example of time traces from such a experiment, and I'm only showing a short and a long distance. This gray region is the cuff oscillations, and then the purple/black thing is the arterial blood pressure. So you can see that arterial blood pressure oscillations are induced during the cuff oscillations, which then cause oscillations in oxygen jockey hemoglobin, both at the long source-detector distance and the short source-detector. So then we can go through our CHS phaser analysis and get those phases of oxygen hemoglobin for each of those source-detector distances. And notice the trend. So we go from short, increasing distance to the longest distance here. And we have oxy versus ABP, which is arterial blood pressure, and then deoxy. So as we increase source detector distance, they become more out of phase, which is consistent with a blood flow dominated oscillation. So this is only for the single distance measurements. Now let's look at single distance and single slope. So here we have single distance intensity as the purple one, single distance phase as the green one, and then single slope intensity as the blue. And let's ignore the difference between cuff and breathing because there's really not much of it. But the point is that as you increase source detector distance in general, you go from in phase oxy deoxy to out of phase oxy deoxy. So you go from blood volume dominated to blood flow dominated. But that's true for single distance intensity. Phase and slope of intensity are basically already at that out of phase relationship, even at shorter distances. So this is kind of hinting at those sensitivity methods I was showing you before, where these other data types, they have preferentially deep sensitivity. And in fact, if you do a simulation where you simulate a blood flow oscillation very deep and a blood volume oscillation superficially, you can recreate the same shape of these. So finally, let's move on to a dual slope measure. So before that was just a multi-distance probe that could not do dual slope. Now we're going to do dual slope. So we do the same protocol, 0.1 hertz cuff oscillation, with a dual slope probe that measures 10 different data types, but we could do 18, but the other ones are kind of not important. So these are some of the traces that we during the same kind of protocol, we have the cup oscillation there. And already you can see that there's differences in these hemodynamics. Primarily, the thing that I'm going to point out is that for the single distance intensity at 35 millimeters, deoxyhemoglobin doesn't change for the oscillator. But then these dual slope measurements have much larger oscillations. Now notice that in this case, we are looking at single slope phase. And this is the only time we publish it because we work really hard to get good measurements of it. But I would reinforce that it is very noisy to the point where really you should just use. So if we do our phasor analysis on all of those, and now we're looking at the phase between the oxyhemoglobin for all of those data types, we see that dual slope is essentially more consistent. And really what might notice in these graphs is that this yellow one is about in the same place phase-wise for all. Everything else might be in a different location. So we say it's a consistent measurement for dual slope of intensity and phase. And then if we look at the more traditional measurement, single distance intensity, in some cases it's completely out and nowhere. It's like time, barely can see it, almost unmeasurable. So we can say an inconsistent or small vector or intensity, but a blood flow because it's out of phase and consistent vector for dual slope. So finally, what we did is we took this same sort of measurement geometry of dual slope, and we simulated a blood flow dominated oscillation, again, as I did before in the deep region, and heterogeneous blood volume oscillations in a superficial region. And you can see, so let me orient everyone. So the green one is the bottom truths. That's what we want to reach. And the blue one is the intensity, and then the red one is the phase. So you can see that already for single distance phase is basically getting the deep one, and the intensity is somewhere else in between the superficial. Single slope is better for intensity, actually a little worse for phase, but that's just because of the particulars of the heterogeneity. And then finally for dual slope, they both are reconstructing the phase of the deep region, but the dual slope phase measurement is getting the right answer. So these are all consistent with what we saw in the actual experimental measurements. So you'll notice that the through line through all of this was all of these measurements indicated that dual slope, particularly dual slope phase, was more sensitive to deep regions, and that those deep regions seem to be blood flow dominated most superficial regions of blood volume. So finally, very short section is the calibration-free the advantage of it. So we applied dual slope to a spectral broadband spectral measurement instead of these measurements in frequency domain. And we did that by basically connecting a dual slope probe to a spectrometer through a fiber switch. And we are looking at retrieving absolute measurements of the absorption spectrum. So the way that we achieve that is we need to know the scattering spectrum first. So we make measurement of scattering at 2 frequency domain wavelengths, and then we extrapolate it. Then using the spectrometer measured calibration-free dual slope measurement. And that extrapolated US prime measurement, we get the absolute absorption spectrum. And we took this instrument and we validated it on a liquid phantom where we changed the absorption of the liquid phantom by adding different dyes. So this first slide is a liquid phantom that's just milk and water. That's the spectrum we measured. Then we add NDA. Then we add a dye with a specific spectral feature, and then a second dye with another specific spectral feature. And the system reconstructed the expected spectral features. So we got this peak here about where it should be, and here about where it should be, about a flat and slightly decreasing absorption spectrum for NDA. And we quantitatively validated it by fitting the measured data for the milk and water phantom to the expected extinction spectrum from milk and water, and we got a R-square of 0.98. So 98% of the variation in the measurement was explained by milk and water. So finally, the last thing we've done is we applied this spectral measurement to static measurements on muscle. So we did that for 3 subjects, and these different spectra are shown for those different 3 subjects. And then what we want to do is we want to take these spectra and we want to fit those spectra to the chromophores that exist inside tissue. So that's oxyhemoglobin, deoxyhemoglobin, water. However, we do the fit in 2 ways. We do it for just those 4 things, and then those 4 things plus some constant. And I'll explain why that is linked. But you can think of that as an artifact, because basically we need to add a constant. And then we also fit the data to theoretical 2-layer models, and we simulated these kind of spectral measurements that you would get from 2-layer models. From all of that, the first thing we can do is we can plot this artifact in the fit versus the layer of the adipose tissue layer thickness. And we see that that artifact increases at thinner adipose tissue. So this is basically like saying that the medium is actually heterogeneous, not homogeneous. And remember, all the theories above are homogeneous medium. So we're getting that constant spectral absorption when you have a 2-layered heterogeneous medium. And we can actually recreate that trend to some extent with theoretical 2-layer models. So the conclusion here is that as far as absolute measurements of absorption go, which we now make calibration-free because that the heterogeneity actually affects the absorption quite significantly. So you'll notice that these numbers are actually very high absorption values. And finally, we plot the recovered values for those chromophore fits versus the top layer thickness. And then we also simulate what we would get. And essentially, we get similar trends for both with the background in the fit, without a background in the fit. And we are able to say that it seems like the medium that we were measuring had higher concentration of oxydeoxy water in the now this is switched. Higher concentrations of oxydeoxy water in the bottom layer and higher concentrations of lipid in the bottom layer. Which is basically consistent with like adipose tissue at the top and then a muscle in the bottom. Okay, so that's everything. And I'll just summarize the 3 parts. So the first part was the different measurement types: single distance, single slope, dual slope, and zero phase. And we did all sorts of theoretical investigations of it. Then we took all those different kinds of measurement types and we applied them to brain measurements, and then looked at the different hemodynamic features superficial relief. And then finally, we apply the calibration-free aspect of spectroscopy to measure absolute absorption, and we found that heterogeneity can actually have a very large impact on the measure of absorption. So that's everything. And I'll acknowledge my family and mentors. And,
Thank you very much. Now, audience.
I know that a significant problem in this kind of diffuse optical imaging is compensating for the varying skin tones of subjects. Could you say a little bit about how your method stacks up with that?
yeah, so actually, that was a reviewer question for this paper, because the artifact that we're measuring here, I'm saying constant background, right? So that kind of sounds like it might be no, pretty constant. But the full slope sensitivity region is mostly insensitive to like a very thin superficial layer. So to prove that to ourselves and to the reviewer, what we did was we did a Monte Carlo simulation where we did basically a layer of melanin, or at least a realistic melanin concentration, and then nothing. And we showed that the measurement that we get for this kind of arrangement is not affected by that thin layer. Now, melanin will affect the signal to noise. So it doesn't affect the retrieve value, but if we have someone with dark skin, we do have higher noise. That's less light. So that is just.
So I had a question about your dual slope imaging. Like you said that 40 millimeters is the maximum. How do you like set that as the maximum? Right? Did you test larger values?
Yeah, it's basically just that with the frequency domain instrument we have, if you consider a phantom or just any medium with the typical optical properties, once you get out to 40 millimeters, the signal is in the noise of the instrument. If you go for 100 counts of the noise, maybe like 10 counts, so it gets a little too much.
Would a better instrument increase that, or just the theoretical limit of all?
It would increase that, although I haven't really seen many instruments that go beyond, like there's some instruments that land and you go up with it. It's very suspicious. And then also, other instruments have another advantage that I should point out when we're talking about this, that are slacks, which is that air range. So the real thing other instruments can help with that air. Because basically our detectors can't measure very short and very long time.
Put that array on a subject, connect the light sources. Is there enough heat energy generated that the subject can actually feel it?
No, there's an ANSI standard for the amount of laser power, and it's very, very conservative. It probably is many times less the amount that you actually feel. Like the intensity of the light coming out of these is actually less than this laser pointer, and I can't feel anything from that laser.
Can you talk about when using dual slope phase is not advantageous?
When you use so big time, well, there's many caveats there. Right? So in situations where it's noisy. Also, we have some work that shows that in particular types of two-layer medium, ozone phase is actually not sensitive deeper than those situation. And A big one is actually that the instruments that are used for measuring phase are complex. So you can implement that also depending on basically any instrument, but those phase is rather special.
Would you think of a scenario with single distance, either right answer for that measurement?
If you wanted to measure this superficial region. But also remember, single distance is heavily affected by any art. So I think the biggest advantage is also the fact that gases are.
That the phase measurements are very noisy. Can you elaborate on what the source of the phase is? What the source of the phase is?
Yeah, the source of the noise is essentially just because the way that the instrument actually works is you have this oscillation, right? And you're trying to measure its amplitude and phase. So then immediately the most obvious way to do that is to take the Fourier transform of it. And pick the Fourier transform of that signal. The phase is it's literally the phase of the complex number you get. And then the amplitude is literally the amplitude of the complex number you get. And if you do error propagation, you'll see that for just some small variation in these measurements, they'll affect the phase a lot more than they'll affect the. There's also other things that affect it, like when you have these oscillating sources, you can have the amplitude noise and the phase noise as separate things. And actually, it's much more difficult to design an instrument with less phase noise because it means that the timing needs to be exact. Like this needs to cross the x-axis right there. Versus we have a lot more fun talking about the it's basically a limitation weights.
I have a question regarding your movement of impulse. So, in case of image reconstruction. Image reconstruction. So you are using movement of impulse.
Yeah.
So, I mean, you could use other technologies like other regularization stuff like singular level composition or probabilization. So was it a decision choice or it's just that we used this?
We did consider other types of inverses. So the more inverse, I think, is more well understood ones, which is one of the reasons we gravitated toward it. We did play with L1 minimization, but the problem is in simulations that works fantastic, but in experimental data it doesn't, because the assumptions that they're less like that there are really just certain number of localized perturbations is really true for our kind of measurements. So we found that we just get the best results for the more inverse, and then that's bolstered by the fact that it's well understood, we can then play around with a lot to understand what to do.
Any other questions? But if not, and the audience is now excused, and then we're going to have the closed session with the committee. Thank you guys one more time. Thank you guys.